This is an additional explanatory section in a short series of presentations to help paraglider and hang glider pilots make better use of Skew T. In this section, we take a more detailed look at the two temperature lines that are plotted on the Skew T graphic. The red one being the environmental air temperature, measured as the radiosonde balloon ascends, the blue line being the dew point temperature. The red temperature line, which is properly known as the environmental lapse rate, or ELR, roughly follows the dry adiabatic lapse rate trajectory until the dew point temperature is reached, and then after that the temperature falls less quickly with height, and the standard trajectory is the saturated adiabatic lapse rate, or SALR. In fact, the ELR rarely follows this idealized path at all. This is because the stability of the atmosphere varies enormously with weather systems, and it also varies considerably with height. The dew point temperature is displayed as the blue line to the left of the environmental temperature line. Dew point can never be greater than the environmental temperature, but the two can be equal and overlap. Dew point is a function of humidity. The radiosonde balloon uses a hygrometer to record humidity as it travels up through the troposphere. Dew point temperature is then calculated using a complicated mathematical formula, and then the temperature is plotted on our soundings trace. Most air around us contains water vapor. Air over the frozen polar ice cap and deserts can be almost totally dry, but in the more temperate environments where we like to fly, air generally contains some water in its vapor phase. The amount of water vapor in air is measured in grams per kilogram of air. At standard atmospheric pressure, 1013.32 hectopascals or millibars, and 20 degrees centigrade, a kilogram of air takes up around 820 litres of space. Typically, there may be around 20 grams of water in its vapor phase within a kilogram of air. Think in terms of around 5 teaspoonfuls of water in an empty IBC. The amount of water vapor contained in a certain mass of air is known as the mixing ratio. The saturation mixing ratio is the amount of water vapor that a certain mass of air could hold if it were fully saturated. In other words, the amount it could hold at the air's dew point for the prevailing temperature. The capacity of air to hold water is significantly affected by the temperature of that air, cooler air having a much lower capacity to hold water than does warmer air. The final technical term in relation to the way in which water vapor is carried by air is the relative humidity of the air. This is the amount of water vapor that is within any parcel of air in comparison to the amount of water vapor that the parcel of air could hold if it were to be fully saturated. Clearly, the relative humidity is highly dependent on air temperature. As we see in this diagram, as a parcel of air cools, then, if nothing mixes or changes, the relative humidity of the air would rise. Cooling with height is therefore quite complicated. This is because the parcel of air will expand, and because of the expansion, it cools. This is why we refer to air cooling with height as adiabatic cooling. However, the water vapor within the parcel of air behaves rather differently. The number of grams of water per kilo of air will be unchanged, and therefore, if temperature was unchanged, the relative humidity of the air reduces as the air expands with increasing altitude. But, as this diagram illustrates, when temperature falls, as we know it does with height, air can't contain as much moisture and humidity rises. The net result of these rather conflicting arguments regarding how humidity, temperature, and dew point are linked is the linear trajectory of anticipated dew point reduction with height, illustrated by the lines we refer to as the saturation mixing ratio lines on our Skew T. The angle of these guidelines is the angle we use as our assumption of the change in dew point temperature as the parcel of air rises. The change in dew point temperature is a reduction of roughly 1.5 degrees centigrade for every 1,000 meters of height gained. This is equivalent to a reduction of around 0.5 degree centigrade per 1,000 feet. Because this change in dew point temperature with increasing height is a lower figure than the change in air temperature by adiabatic cooling of unsaturated air, the so-called dry adiabatic lapse rate or DALR, then the lines we apply to predict when a rising parcel of air will condense will inevitably and always converge. Indeed, because we always apply a standard rate of temperature decline to each of the two key temperature figures, the dew point and the air temperature, then we can predict how far above us the two lines will meet if we know the air temperature at our height and the dew point. The simple formula we can use to calculate how high above us cloud will form is shown here. We firstly calculate the difference between the air temperature and the dew point temperature. In this example, it's 25 degrees. Then we divide the figure we have by 2.5, then multiply the outcome by 1,000. In this example, we would expect Cloudbase to be 10,000 feet above us. This is the predicted convective Cloudbase in feet above the height that the two temperatures have been measured. In the example illustrated here, the valley floor is humid and cool. This is frequently the case early in the day when the ground has given up more heat overnight than the air, and when there are rivers or lakes in the valley floor, or if there has been rain overnight. The temperature spread is therefore rather artificially reduced by the cooling of the air close to the ground and the high relative humidity. If we were to use these two temperatures to assess expected convective cloud base for the day, we would underestimate the altitude. However, having travelled to launch and having moved up into atmospheric conditions that are much less affected by the ground surface conditions, the estimation of convective cloud base gives an outcome which is 500 feet higher. In this example, the standard trajectory of reducing dew point temperature and the standard adiabatic cooling would suggest convective cloud could form 5,600 feet above the launch at 2,000 feet. However, we can see from the soundings records that any convection will stop rising at around 4,800 feet as the environmental air temperature stabilizes between 10 and 12 degrees and eventually becomes isothermic with increasing altitude. Similarly, the air becomes significantly less humid at the inversion, and this will be a blue day with good thermals but no convective cloud.